So that looks like recording. Let me make this big. It goes away. Oh, look what I found. There is a little trick you can do to do like a cursor things, and I can actually point to things. I can make it go away. All right, so where did we end the last time? So we were working on a harmonic oscillator, right? So let's just do a very quick recap. It was a 1D, the simplest physics-based system you can think about, right? So that it lives on just one dimension, so there's just a position x, right? At time, there's like a particle, which has some mass. We say that the mass is always unit, m equals 1. That's what I will be using all the time, by the way, unit masses. And at time t, the particle has position xt. I will go quick because this is just a recap, right? And we said that the force that acts on that particle depends on the current position of the particle, and it's minus x. That's a Hooke's law with the stiffness coefficient 1, okay? And as we discussed the last time, this leads to a system of linear ODEs that can be written like this. So there is some A matrix, and that's ZT. Maybe I'll just remind you the notation. So what this Z was, that was a concatenation of X dot T, V dot T. So this is a 2x1 vector. The A matrix is the minus 90 degrees rotation matrix. So that looks like this. And this is just the XT and VT, okay? So this is exactly the same thing. So this is just a different notation to that, okay? So that is clear, right? If you have any questions, just interrupt me. And what we are solving is an initial value problem, IVP. That means that for given Z0, okay, so that's the initial position and velocity. We say we start simulating at time equals 0. So those are the initial conditions. Those are given. And then this system is a system of linear ODEs, so it has analytical solution. Okay, that's usually not going to be the case, but it's very helpful to first consider this simple example where you actually can solve it analytically, even though in practical situations you cannot solve it analytically. Okay. So in this case, the analytical solution is given using the matrix exponential formula, e to the power of ta times z0. Those are these initial conditions. And this e to the power of ta, that's the matrix exponential. That's what we were talking about the last time, right? And we also said that if I have a matrix and I have its diagonalization in the form of v lambda v inverse, then you can write the exponential of that matrix as v e to the lambda and v inverse, okay? And this is easy because this is just a diagonal matrix, okay? So the exponential of a diagonal matrix means just exponentiating each of the numbers on the diagonal, okay? Again, I'm still repeating what we were saying the last time, okay? Because what I want to do, I actually want to solve exactly the system of ordinary differential equations, so you get the perfect solution of the motion, the analytical solution, okay? And then we look at the solution and we ponder some of its properties, basically understanding what motion means. Okay, so to get this diagonalization, what we need to do, we need to compute eigenvectors and eigenvalues of A. Okay, here I wrote it for some arbitrary matrix M, but we are interested in this specific matrix A. That's our A here. And we already said the last time that eigenvalues of A are plus and minus I. Okay, they're complex eigenvalues. That's no surprise because the matrix is a rotation, so it has complex eigenvalues. And now what we need to, and that's basically where we stopped the last time, right? So now we need to find the eigenvectors. So eigenvectors corresponding to the two eigenvalues, 2 plus minus I, okay? So let's go do the first one. So let's say the eigenvalue number 1, lambda 1, is plus I, okay? It's the plus complex unit. And we are looking for the corresponding eigenvector. So that eigenvector is going to be some vector v1, which is going to be a complex two-dimensional vector. And that vector has to have the property that A v1 equals I v1. Okay? So that means what we do A minus I identity, right? And we would like to find a v1, which is in the null space of that matrix complex vector. Are you still with me, or I'm going too fast now? I'm trying to overcompensate for going too slow the last time. So feel free to interrupt me at any time, okay? So we'll do this. So we'll take this matrix and write it out. So that matrix, I was gonna disable those things and I forgot. So that matrix looks how? Minus I, 1, minus 1, and minus I, right? This is the A minus I identity, okay? And now what I need to do, let me call them, I don't know, X and Y. And I need to find this vector X and Y complex, which is in the null space, okay? So how do I do that? Maybe I can give you a chance to speak a little bit. My pen. So that's like a standard linear algebra problem. Give me a vector in the null space. How do you do that? There are actually several linear algebra tricks which you can pull off if your linear algebra is strong with you. The first thing is that this matrix A minus I identity needs to be singular, because that's exactly how we found the eigenvalues, right? If it was not singular, then the only solution would be the trivial one, x equals 0, y equals 0, and that solution is no good. Why? It's trivial, yeah, and that's exactly what's not allowed for eigenvectors, right? Zero vector is not a valid eigenvector because it always satisfies this, so it gives us no useful information. So that's why the definition of eigenvector specifically prohibits that case, okay? So that's no good, right? Well, so what we can do, so because the two rows are linearly dependent, what we can do, we can do a simple thing. We can just pick whatever we want. We can pick x equals 1 and solve for y. Okay, so if we pick x equals 1, then the first equation will give me what? It will give me minus I plus y equals 0, right? And that looks like that y then needs to be I, right? So I have a vector, so that gives me vector v1, which looks like this. It is 1 because that's what I picked. That's this thing here, and I. Okay? Now we can verify that this v1 with dot producted with, okay, this is slightly, dot producted with the second row of the matrix should give me also 0. So let's try to check it quickly. So that's so that will be minus 1. Right, and now we have to use the fact. Right. So that's minus I squared, but I squared is minus 1, so that's plus 1, so that gives me exactly 0, so that works. If it didn't, that means I made a bug in computing the eigenvalues, because for the eigenvalues they need to be linearly dependent because the matrix is singular. That's what we said, that's how we found the eigenvalues to begin with. Okay, so yeah, so we have the vector AV1 which satisfies exactly this equation, and this is the v1. This is its exact value. It's defined up to scale. I can scale it by arbitrary complex number. It will still be a valid eigenvector unless I decide to scale it by 0, which would not be a very good idea. All right, so that's one of them. So let's do another one, because there needs to, so that was for the plus I, right? We need to have the other one for the minus I. So let's do the other one. So lambda 2, that's the second eigenvalue, which is minus I, right? So again, I do A minus, so that will be plus I identity, right? Which is what? Which is, let me write it separately. Let me write it here. So the matrix will be plus identity, so it will be I, 1, minus 1, I, right? Let's go back. That's actually the advantage over the whiteboard, because once you erase something on whiteboard, it's gone, but here we can easily switch to different boards. So that's what, yeah, so I'm looking at this thing here, right? And now just the minus i's become just plus i's. So that looks correct. And now the ideal is the same. I still need to find some x and y such that this will give me 0. So again, find a vector in the null space of that matrix, right? So again, I can do exactly the same thing. I can say, let's pick x equals 1. Again, why can I pick just whatever I want? I cannot pick whatever I want, right? I cannot pick 0. Why I cannot pick 0? Just to drive that point home. Because if I pick x equals 0, exactly, Trevor, if I picked x equals 0, I will get y equals 0, I will get a trivial solution, which is no good. Yes. So I can pick anything else that's non-zero. Well, why make my life more difficult than necessary and pick x equals 1, okay? So in that case, the first equation, so if x is 1, then the first equation says I plus y equals 0. Everybody agrees? That's the first part. So that must mean that y needs to be minus I, right? So that tells me that the second eigenvector v2 corresponding to the eigenvalue minus I will be 1 and minus I, okay? And sure enough, you can verify that AV2 equals minus I v2, okay? So that's good. Now we have the two eigenvectors. So we can put them together. Okay. Now we can diagonalize the matrix and then compute its exponential. Okay. So by putting together, I mean we just do this, v1 and v2. And if I just put it in a matrix form, so the A is a 2 by 2 matrix, right? Now this is also a 2 by 2 matrix. Now this is a complex matrix, but that's okay, right? Complex numbers are just more general than real numbers here. And this is just rewriting these two things with v1 and v2 in one shot, okay? And to make this be actually true, I need to put the eigenvalues here, okay? So all these things obviously are 2 by 2 matrices here. Is this clear to everybody? Where did that come from? This is just a matrix multiplication. So it's just a matrix way of writing these two equations. AV1 equals lambda 1 v1 and AV2 equals lambda 2 v2. And please forgive me if I'm sloppy about the arrows, because it's annoying to put arrows over all vectors. So just try to remember what's a vector and what's not. Like here I should have put in all the arrows here, but I didn't, okay? So this is exactly equivalent, okay? So the nice thing here is that now I can just write it in matrix notation. So I will call this matrix V. So that will be the matrix of eigenvectors V, and this will be the diagonal matrix of eigenvalues lambda. All right. And now I almost have a diagonalization, right? Because this thing can be written like this, right? Notice that lambda is a diagonal complex matrix, so that's all cool. And all I need now to do a diagonalization is that I need to find the V inverse and write it in this form. Okay, then I'm done diagonalizing, then I can compute the exponential and I will get the exact solution of the motion. All right? Cool, so how do I compute the V inverse? There is a little trick I can pull off here, because this matrix is a almost unitary matrix. So I can just do, so this is actually 1/2 of V conjugate. Do you know what's a conjugate matrix? If you do, you can just say it. It's like transpose, but in a complex domain. Turns out that when you are in a complex domain, then transposition isn't enough. You also want to conjugate all of the complex numbers, and conjugation meanings. Yep. Sure.
Is there a distinction between conjugate matrix and Hermitian matrix?
I think that's the same thing, if I'm not mistaken.
Okay,
that's
I've just in other classes sometimes.
Yeah, Hermitian.
I think you don't do the transpose, you just transpose the complex value versus a Hermitian where you transpose the matrix and take the
right.
conjugate.
I think you're right that the Hermitian is another term. Actually, the full term would be conjugate transpose. And that's exactly what I meant by this star. You know what? Let me write it out explicitly so there is absolutely no confusion. So what I'm gonna do, I'm gonna take this matrix V. Okay, maybe I should first write it, right? So I guess it's kind of obvious because so the V1 was 1 and I, and the V2 was 1 and minus I. Okay, so the matrix V looks like this. And if I transpose it, so now I transpose and conjugate, okay? Okay, I can even do it like kind of slowly. If I transpose, I get this, right? So rows become columns. And then if I conjugate it on top of it, so that's the conjugate transpose or Hermitian matrix, so then I also flip the signs on the complex units. That's what conjugation is, okay? So that I can now write here, 1 minus I, 1, and I. This 1/2 is there because these vectors were not unit, okay? The length of the V1, and what was the length of the V1 and V2? Oh, you have a question?
I just had a question,
yep.
Sorry. So to find the complex conjugate, you take the transpose and then flip the sign of each complex.
Okay.
Right?
So there are two things. There's the transposition, which is for matrices, where rows become columns, columns become rows. Then for complex numbers, and it can be just a complex number, just a single complex number, no matrix, okay? You can conjugate that by flipping the sign on the complex part. That's conjugation. That works even for complex numbers. But the Hermitian transposition, I'm not really sure what's the best. Conjugate transpose, I would say, means both transpose and conjugation. And that's what you want to do if you are dealing with complex matrices. That's the long linear algebra story short. Okay? Thanks. Good question. And the 1/2 is there because the length of V1, what is the length of V1, the norm? It's not the unit, which what I would ideally want, right? The length is square root of 2, right? Because both of the parts have length 1. So that's why I had to put here, this is slightly annoying, I had to put here this 1/2. So I actually, so when I actually do this, weird. So when I actually compute the V inverse, then I want to get an identity matrix, right? If I didn't put the 1/2, I would get 2's there, right? So that's why that factor is there. Anyway, what really matters right now is that now we have the decomposition. So if you want, I can write it out explicitly. So this was our original A matrix. It's gonna be later multiplied by a scalar, and I can write its diagonalization like this. So this is the V matrix here, 1, 1, I minus I. Here come the eigenvalues, I, 0, 0, minus I. And here is the conjugate transpose, 1 minus I, 1, and I. Okay, so indeed this is my A, this is my, I'm just writing it all again just to put it together. And this is V conjugate. Okay, this is my diagonalization. Now I can use this to compute e to the power of ta. Okay, because what we said before is that this will be equal to, this is the 1/2 from here, this is this 1/2 thing here, and this will be 1/2 of v e to the power of t lambda v conjugate. Okay? So let's now compute this, what that is going to be, okay? So the first thing I can do, I can just leave these terms there. So this is gonna be, you know what, let me just do it all together. Let me move on to another page. Let's do this trick here. Oops, didn't work. Copy. Oh, come on. Paste. And we'll continue from here, okay? So what we are gonna do, we are gonna plug there the values of the matrices. So we know what V is. V is 1, 1, I minus I. Now, what is gonna be the exponential? Well, we know that the lambda matrix is a diagonal, right? So this is going to be e to the power of ti, 0, 0, e to the power of minus ti, okay? And here is the conjugate transpose. So that is minus I and I. All right, everybody cool with that? Nice. So what I'm gonna do now, I'm gonna just work out the product. Okay, so let's first do the product of these two matrices. It will first become a horrible mess, but then it will crystallize into something quite beautiful. So watch this carefully. So this will be 1, 1, I minus I. I'm just copying that, and now I will just do the matrix multiplication, right? So this will give me ETI. That's the first. Yeah, it's not really that as convenient as pointing with a finger, unfortunately, this thing. I was gonna do like this. I was gonna do like first row with the first column. It's always annoying to be switching to this thing. Oh, well, I'll get better at it. So then the second one is what? It is minus IE to the power of TI, if I'm not mistaken. Then the next one here is going to be what? E to minus TI, looks like, right? And the last one is going to be IE minus TI. Does that sound right? So that's just a multiplication of complex matrices. Now, is that cool? So now, let me erase this thing. So now I will multiply the remaining two matrices together. It will get a little bit hairy, but just for a moment. So the first term will be what? It will be ETI plus E minus TI. What's going to be the second one? That's going to be minus EIT like this. Maybe let me just write it, because saying it is kind of awkward. Plus this. Okay. Then the next one will be what? ETI minus like that. And here we have to multiply the complex units, right? So minus I squared looks like plus 1 to me, so this will be ETI. And again, minus I squared looks like plus 1, so this is plus E minus TI. All right? Does that look correct? Lots of minuses and i's to keep track of, so I hope I got that all right. We will see in a moment. So how to turn this mess into something useful? Any ideas? So far it looks terrible, right? Like sometimes when you do math, if you get into like something where like screw that, that's not gonna be helpful. Huh? Exactly. Euler's formula. That's exactly what we are gonna use. So what is Euler's formula? Exactly. So yeah, let me write it down. E to the, so if I write it directly for what we need here, that is cosine of t plus I sine of t. Okay, that's how we can actually get rid of all the complex things eventually. So if I apply the Euler's formula to e to minus ti, well then of course I just get, so cosine of minus t is cosine of t, right? Sine of minus t is minus sine of t. So let's just do that. If I multiply it by I, then I get just the thing multiplied by I, right? So I cosine of t, and now this is minus sine of t, right? Do you see the beautiful symmetries of these algebras? e minus ti, so that I'm taking the second one and multiplying by I, so I get I cosine of t, and here's going to be plus sine of t. Okay, so I kind of prepare the Euler's formulas for all of the terms that we see here, and then we can see something quite cool. Let's just apply it here, and I guess let me grab my cursor thing here. So what is the thing? ETI and E minus TI. So ETI is this, and E minus TI is this, okay? So if I sum them together, looks like to me, what do I get? Not square, they are summed.
Oh, right.
Two cosines, exactly. Two cosines of t. Perfect. Now, what if I work out this thing? So this is this minus EI TE, so I will be subtracting this guy, right? And I will be subtracting it from that guy. So I'm taking this minus this, okay? So what does that look like to you? Two sines, right? I agree. Two sines of t. Okay. Now, I should probably find some app that just displays the cursor all the time, right? So you can do it with jailbreaking the iPad, which I don't want to do. So that the cursor was there at all times, like in a computer. That would be awesome. Anyway, I'll look into that later. So now this guy here. So ITI is this, and I'm subtracting. Oh wait, that, right? So is that right? So yeah, this one minus this one. So it's actually a very similar idea as before, except that I get a minus there, right? That's all good. So here I get minus 2 sines of t. All right. And the last one, that is, hey, the last one is the same as the first one, so that's again 2 cosines of t. All right. So now you can see how this thing nicely plays with these 2's here, so that actually completely cancels out, and all I'm left with is this cosine t, sine t, minus sine t, and cosine of t. And that's what is that? That's a rotation by angle minus t, right? Because in general, you know that the rotation matrix by angle alpha is a cosine of alpha minus sine of alpha, sine of alpha, and cosine of alpha, right? So here we just plug the negative angle. That just means we are rotating clockwise as opposed to counterclockwise, which is the convention for a positive angle. Okay, so that's quite beautiful, right? Because that means that the complex numbers were essentially just like an intermediate thing, and eventually we got to some nice, easy, real stuff. Mm-hmm. Oh yes. That's kind of, that's basically so the question basically is how does to repeat it, Euler's formula relate to the unit circle in the complex plane, right? So this is like the real part here. This is like the complex. How do you? Oh, imaginary, right? That's how you usually call it. The imaginary one, right? And then you have the unit circle. Oh, you know what? I have a circle drawing tool here somewhere. Watch this. I probably even have a line drawing tool. I'll get better at using that as we go forward. So yeah, so the Euler's formula is exactly this, right? Because if you take some, oh, it's still doing that. I have to disable that. So if you take any complex number, I want to call it Z, let's call it, I don't know, P. So then this thing is exactly the cosine, right? And this thing here is exactly the sine. So that's really what it is. And you could also give it, but that's just like going back to like explaining complex numbers. So what is important for us here is that now we have a solution to the differential equation. Okay, so now we have a perfect analytical solution, and that solution looks like this: zt rotation by angle minus t, that's our time, times the initial conditions. Okay, we can work it out if you want to get the positions and velocity separately. So that just means applying that matrix. So that will be x0 times cosine of t plus b0 times sine of t, and the similar thing for vt. So this will be now minus x0 times sine of t plus v0 times cosine of t. Okay. So let's play with this a little bit, or let's look at some specific initial conditions. Okay, let's say that my initial position is 1, and let's say that my initial velocity is 0. Okay, so spring-wise, that corresponds to the situation kind of that I was drawing before. This is my 0, that my mass point is at position 1. There is this Hookean spring connecting it together. There is 0 velocity in the beginning, and I just release it and let it go, right? And these formulas tell me exactly what the motion will look like, right? All I need to do is to plug in this, and if I do that, I will get that xt equals cosine of t, and vt equals minus sine of t. Okay? And I have these guys plotted for you. So be nice if it remembered the folder where I was before. This one. So that's how that plot looks like. So again, that's the situation for harmonic let's do this. So that's the harmonic oscillator. This is my 0, right? It started at 1. There is like a spring kind of connecting that together. So that this situation corresponds to this point here. So the blue thing, that's the position, right? That's the x of t, and the red thing is the velocity. So the red thing is the v of t. Oh, actually, I could do it nicer. This is just me playing with this app. And this is x of t, and this will be v of t. Okay, how about that? So where we start, so this is time equals 0. Okay, this is time here. So at time equals 0, I said that those are the initial conditions, right? We said that x at 0 is 1 and v at 0 is 0. So it starts with 0 velocity and it's pre-stretched, right? The spring has the rest post length of 0, so the spring would like this point to be in the origin, but it's not there, and that's why we get a motion. Okay, and let's look at the motion. I mean, intuitively, I guess it is clear what the motion will look like, right? It's exactly a harmonic oscillator. So if I was to animate it, this is like a really toy case of a physics-based animation. So here's actually, whatever. So it starts here with 0 velocity, right? So then it starts accelerating, and then bouncing back, slowing down, and again. So the motion will look something like this, okay? And this is like a motion which you can render out, right? And you have your first physics-based animation. That's a oscillating motion. It's a very simple motion, but it turns out that the more complicated motions are kind of similar to this case. It's actually not that much more complicated. So let's look at what the curves do exactly, right? It's kind of cool to trace that point as it goes along. So this means the time goes on, right? So we start here and then we go down here. So at this point, at what time? What is the interesting time here? Pi half, exactly, Brian, that's right. So at pi half, I have x equals, let me even write it down actually to make it clear. Where shall I write it? Let me move this away. Erase this thing. So for x, for pi half, this is 0, right? And v of pi half is how much? -1, exactly. So does that make sense? So that means that the point has returned back to the origin now, right? And the velocity, so the x-axis is pointing in this direction. So indeed, the spring pushed it back, and the point is shooting with the maximum velocity it will ever achieve, or the maximum speed, I should say, because the velocity is negative. That's the only sense of orientation you have in 1D. It's either positive or negative. Once we go to more dimensions, then you can move in many directions, but here you only have plus and minus for 4 directions, okay? So that's the case when the particle was right here, okay? And then it keeps going, right? Now at this point, and by the way, this could easily be new initial conditions, right? I could say, hey, those are my initial conditions, position 0, velocity -1, right? And I would again get a solution which would look exactly the same, except would be translated to 0, right? That's obvious. So that means the show keeps going on. So at that point, the spring will keep extending up to this point, and it stops while the position reaches -1, right? That happens. So the previous one was at pi half. The next interesting event happens this exactly pi, okay? So when I am at pi, at time pi, so that x of pi is what? -1, that's right. And v of pi is how much? 0, exactly. So that's a symmetric situation to what I started, right? I'm on the opposite side, the velocity is again 0, and you can guess what's gonna happen next, right? Then the motion will indefinitely repeat itself. And that's exactly what the sine and cosine curves give us, okay? So here is another cool thing I would like to bring up on this example, and that's energies. So we have 2 fundamental energies associated with mechanical motion with dynamic systems, and that's kinetic energy and potential energy, okay? So the kinetic energy, what is the kinetic energy? I will sometimes write it as K. Depends only on the velocity, okay? And in our toy system, what is the kinetic energy? That's really basic physics. You must have.
Is it 1/2 v squared?
Yep. 1/2 of v squared, yes. In general, it would be 1/2 mv squared, but we said that the mass is 1, not to complicate things with more letters. So this is indeed really just 1/2 of v squared. That's what the kinetic energy is. Do you know what potential energy is? Potential energy is slightly trickier. I will just write it as E, as energy. Some people denote it as V or something like this. I think those people are called physicists. So the potential energy is defined for any conservative force. Okay, in this case, we do have a conservative force. That means that the force can be written as the gradient of a potential. Okay. The Hookean spring is an example of a conservative force. What is some other example of conservative force? Just to quickly brush up your physics know-how.
Simple, just height, how high you are in gravity.
Exactly, that's right, Trevor. So another example of a conservative force is gravity, exactly, because it's also defined by a gravity potential, exactly. What would be examples of non-conservative forces? that you cannot find a potential function for them.
Friction.
Exactly. Friction would be an example of a non-conservative force because that loses energy or depends on the path. So in this case, the potential energy is actually super simple. Do you know what in this example the potential energy is? No, there's no gravity here. This is 0g and this is 1d land. Hmm? Correct. And I said the k is 1, so this is half x squared. Correct, British. Thanks.
What was K?
K was the stiffness. So that's the Hooke's law says that the force is proportional to this minus stiffness position, minus kx. But I said, let's not bother with these k's and m's. Let's just say it's 1 to make this formula simpler. I think pedagogically is the right thing to do. So we just said the stiffness is 1. Now the stiffness could be used to model like stronger versus weaker springs if that's what you are into. So why is it 1/2 x squared for the unit stiffness? So let me actually make a note here. Unit mass and unit stiffness. Why is the potential energy like this? Because we said what forces are, right? We know that force is so the force is minus the derivative of the potential. That's really what the potential is there for, right? So if I do the minus derivative, I get minus x, which is exactly the Hooke's law for the unit stiffness. So that's why this is indeed the potential function. Okay? You could say also that the potential function is the antiderivative of the force, if the force is conservative. All right. So now let's take a look what these energies do. So what are the potential and kinetic energies here at t equals 0? And let me even write it down. So when we are at t equals 0, what are the values of the kinetic and potential energies? So by the way, this thing is to be understood, of course, this thing and this thing. The v is always understood as a function of time, right? So I could also write it as kvt equals 1/2 vt squared, right? Because since the velocity and positions depend on time, so will the kinetic and potential energies. And notice one important thing that will be very important in the following, that the kinetic energy depends only on the velocity, and the potential energy depends only on the positions. All right, so at time equals 0, what is going to be, I can call it the kinetic energy of 0, if you understand it's the kinetic energy of the velocity at time 0. So what is that? That's kind of simple, right? That's 0. And the potential? 1/2, right? So if I go to time pi half, right? That's what we have here. What is the kinetic energy now? Almost? Yes. Kinetic energy at pi half is exactly 1/2. That's right, Jessica, right? And what is the potential energy at the time pi half? 0, exactly. E pi half is 0, right? And if we go even further to time pi, what do we have there? The kinetic at time pi is what? Again, 0, right? And the potential at time pi is 1/2, right? So notice one important thing about those energies, they are always non-negative, right? That's not the case for all potentials, it's the case here. It's always the case for the kinetic energy. The kinetic energy cannot possibly go negative. The potentials can, like the gravity potential, you said that can easily go negative. All right, so here is an interesting thing you can notice. What is the interesting thing you can notice about those two energies? They are being conserved, exactly. So the sum of the kinetic and potential energy is always a constant. And that means that the total mechanical energy, the sum of the kinetic plus potential energy, is constant. Okay? I actually plotted that just so we can look at the graph and appreciate the... Should really do this with fewer clicks, but maybe I can just... I plotted them for you too. So this thing was the kinetic energy, right? The first, wait, no, this was the potential energy as a function of time. And this one was the kinetic energy as a function of time, right? All right, it started with velocity equals 0, so that's what it is, okay? Actually, what these functions are, it's kind of easy to write it, right? So the potential one is, what is the potential as a function of time? Well, the position was just sine, right? Then maybe we can go back and see where we had it. So this we had the solution right here, right? Oh, not sine, right? So the potential will be what as a function of time? The potential is 1/2 of x squared, right? So if the x as a function of time is cosine of t, it will be 1/2 of cosine squared t. And that's exactly what I plotted here. So this is 1/2 of cosine squared t, okay? And the kinetic one, similar story, right? If I can go back here, and oh, it's kind of easy to do with a finger. So the velocity is minus sine t. The potential, the kinetic energy is 1/2 of the velocity squared. So that's going to be what? Exactly, 1/2 sine squared. 1/2 sine squared of t. And those are exactly the functions I have plotted on this graph. Okay, so this is the cos 1/2. You can see this is 1/2, 0.5 cosine square, and this is the kinetic starting from 0, and that's a sine square. Okay, and of course you know from basic trigonometry that if exactly right now when you see cosine square and sine square, then you should be itching to sum them, and that's what you can indeed do. So if you do the total energy, then you of course see it's 1/2 of cosine squared t plus 1/2 of sine squared t, but you know very well that this is 1, so this whole thing is always 1/2. So this blue curve plus the red curve, they sum to, watch this, to a constant 1/2, almost there. Should be really, should be really, oh, never mind. It should be at 1/2. Okay, and this is a fundamental property of all mechanical systems, that the total energy is conserved. And the total energy is so important that it has a name. It is called the Hamiltonian, and it's a function of both position and velocities, and it's simply the sum of the potential energy plus the kinetic energy, okay? And I can also, of course, again, so you're not confused with all these letters, it is also varying in time, just like the energies themselves, right? That's always the deal when we are solving differential equations. So I can also write it like this, and I can study how does it change with time, okay? So I can either look at it as a function of positions and velocities, or I can say that the positions and velocities themselves are a function of time, and therefore the Hamiltonian itself is also a function of time. Okay? So Hamiltonian is just a fancy name for total energy. And that goes back to William Rowan Hamilton, the genius Irish mathematician who also invented another fun trivia quiz, another cool thing in graphics. Yes, quaternions. And he probably invented many other smart things too, but Hamiltonian mechanics is the same guy. All right. So yeah, so I can, using the Hamiltonian, I can say that this is always constant, okay? And that is true not just in our toy case. This is true for any conservative forces. For any system you can write in this using a potential using Ex, then the energy will be conserved. And I will prove that in a moment. But first, I want to show you what Hamiltonian mechanics is, which is something that can be pretty scary if you open some physics book, but it actually is not very complicated at all. It's just rewriting the equations of motion using the Hamiltonian. That's all there is to it, okay? So let's still stick with our pedagogical didactic toy case, the 1D1. Then I will generalize it to n dimensions, actually not that much more complicated, okay? So basically the point here is that the Hamiltonian is all you need to know to characterize the motion, okay? It's kind of philosophically, it's kind of saying that you can start from the notion of kinetic and potential energies and work from it, okay? So that was exactly Hamilton's idea, and this is called Hamiltonian mechanics. So let me write again the traditional Newton's equations of motion. They look like this. You remember very well that the dot is the time differentiation, right? And now I have the Hamiltonian, x and v, which is, as I said before, is the sum of potential energy and the kinetic energy, okay? Again, notice the separability, right? That the potential depends only on the positions x, and the kinetic energy depends only on the velocities, okay? So now I can do a cool thing. I can take the gradient of the Hamiltonian. So what does that mean? That means that I differentiate first by x and then by v, okay? Well, if I differentiate by x, then it means that only this term is relevant, right? So I only get the derivative of x. Then I differentiate by v. That means that I'm differentiating the kinetic energy by v. And what is that? The kinetic energy is really nothing fancy, right? The kinetic energy is this 1/2 of v squared. So what is the derivative of this? V, right? That's all there is to it. So the gradient of the Hamiltonian is the minus force. That's the derivative of potential and the velocity, okay? Like more abstractly, you could say that the gradient of the Hamiltonian is a function from R2 to R2 for any point in the phase space for a position and velocity. It returns another 2D vector, okay? By the way, so now I'm talking about general potentials, E, okay? For our harmonic oscillator example, what is this map? What is the gradient of the Hamiltonian? So we said that for the 1D toy case, we said that E of x is 1/2 of x squared. And we'll be now considering more general potentials than this. But for this specific potential, what is the gradient of the Hamiltonian? So first, in this case, the Hamiltonian is just the 1/2 of x squared plus 1/2 of v squared, right? So the gradient of the Hamiltonian here is what? It's the, if I look at it as this mapping from R2 to R2. Well, that's the level set of the Hamiltonian. That's the very next thing I was gonna explain. You're right, the unit circle is there, kinda, but that's the level set of the Hamiltonian. I'll get to that in a moment. Now I'm asking, what is the gradient of the Hamiltonian? It's like for you medical imaging guys, this is your bread and butter. What's the gradient? Because the Hamiltonian indeed can be seen as a function that defines level sets and gradients, right? Here it's something super simple for this case. I just want you to get like the abstract understanding of this R2 to R2 function as a mapping from a 2D vector to a 2D vector. Just kind of, I guess, the main idea of the Hamiltonian mechanics or Hamiltonian formulation of Newtonian mechanics, if you will. There's no like relativity or quantum. It comes up in quantum mechanics too, but that's not what we are doing, okay? Exactly. Yeah. So this map has a name. It's called the identity. Okay. So in this toy case, the gradient of Hamiltonian is identity. Exactly, Trevor. Yeah. That's just xv. So that's what it is. But the beauty is that now I can move beyond the toy case and I can say that this potential E can be anything, okay? So the kinetic energy is always going to be this, but then this E can be whatever, okay? I mean, it should have it should be differentiable. It should be continuously differentiable if I want something reasonable out of it, but it can be definitely much more general than 1/2 of x squared, okay? And now here comes the Hamiltonian formulation, okay? So this matrix, which we have seen in the toy example, actually appears there again, even though now I have moved beyond the toy example, okay? Now the potential can be anything. And now what's going to be here is the gradient of the Hamiltonian evaluated at zt, okay? Let me just remind you that the z was a function from r plus, from time to r2, okay? That's the positions and velocities concatenated in a 2D vector, right? The gradient of the Hamiltonian is an operator which goes from R2 to R2. So this consumes, so this Z takes time, that's the T. I also wish this cursor was smaller. It produces R2, and then this produces another R2 vector, which I can multiply definitely by a 2x2 matrix, right? And this is another 2D vector. So at least like doing a syntax check, and it all checks out, okay? And this is the Hamiltonian formulation. This matrix is sometimes denoted as J, okay? So I can write it simply like this, just Z of T. And those are Hamilton's equations. It's actually a simplified version of Hamilton's equations. I made things a little bit simpler here by assuming that the masses are constant and unit, okay? For constant and unit masses, okay? Since we are not doing rocket science here, I will just keep the masses constant. This pun is intentional because if you have something like a rocket, it actually changes its mass and you need to model that. But in physics-based animation, you rarely need it, and especially when you are first looking at it, I think pedagogically it's better to just look at the simplified version. You already have like all the complexity there, and no longer assume that the potential is this simple function. The potential now can be arbitrary continuously differentiable function. Okay. So this thing is kind of just like a silly rewriting, right? You can immediately see that this really is equivalent to this, okay? That's because we know, maybe let me get the cursor here. That's because we know that this is this, right? And if I just work out the matrix multiplication with this special kind of matrix, with the J matrix, then in the first row I get just v, right, which is a function of time, so I recover exactly the first equation, and the second I have this e prime, that's what the gradient gives me, times -1, so I recover exactly the second equation. So these things are trivially equivalent, okay? So this J, that's exactly our A matrix from the toy case, okay? And why this happens to coincide with the toy case is because in the toy case, that's what I wanted to see there. We are recording, that's good. And zoom. All right. So now I upgraded the function. So before we were saying that n was 1. Now I'm just going to a general dimension. Actually, it turns out that it's not much more difficult, right? The deal is still the same, that the velocity is still the time differentiation of the positions, right? Now this function has n dimensions, but that doesn't matter. You just differentiate every single component of it separately by time. That's how multivariate calculus works. Now, and we can still have a potential energy, and the potential energy now goes from Rn to R, so that's our potential. Notice that it could possibly be negative too when we'll talk about elastic potentials. That's what we will talk about later, like mass spring system, finite elements. Those will typically be non-negative. But if you have a potential like gravity, that can go negative. So we don't have to make any assumptions other than that being a continuously differentiable. And then we still have a kinetic function, a kinetic energy function, which also goes from Rn to R, but now this Rn is understood to be velocities. And now the kinetic energy is always not negative, and if the v is now an n-dimensional vector, and let's again say that all masses are 1. Okay, all masses of all particles are unit, to slightly simplify the formulas. So what is the general potential function? Now this v is a vector. If you wanted, I can give this a little arrow. I can give this arrows everywhere, but then it's kind of annoying with the dots, right? So I will not always be writing the arrows. But how does the formula change? Before it was 1/2 v squared, right? Now v is an n-dimensional vector, so what do you propose? It's kind of simple. It's just the sum of the kinetic energies of all the particles. Every particle has mass 1, so I can write it as 1/2 the square norm of the vector b. Okay? That just means take the first component, square it, plus the second component, square it, eventually divide it by 2. Okay? So that's the kinetic energy function we'll be using, assuming all the masses are constant and 1, right? Again, the same kind of deal. I can also view the potential energy and the kinetic energy as a function of time, just like in the 1D case, right? And I can have a Hamiltonian function of x and v, which is again nothing but the sum of the potential energy plus the kinetic energy. Okay? So now x and v's are vectors, but the formulas look exactly the same. Okay? Now the Hamiltonian is a function from 2n to r, 2n because there's positions and velocities. Okay? Now the gradient of the Hamiltonian is still a reasonably defined operator. Instead of being from R2 to R2, it's now going to be what? R2n to, yeah, to R2n, exactly. And the gradient of the Hamiltonian basically means, now it's slightly trickier, right, because that's a multivariate differentiation, but that it means it's the gradient with respect to x of the Hamiltonian and the gradient with respect to the velocity part, okay? So it's still very much the same thing as before. Now I have, so again, the Hamiltonian is separable, right? So this is just the gradient of the E part, because the kinetic energy does not depend on x at all. And the difference, so this is a multivariate differentiation, but the result is basically the same thing. The result is again just v, except that now the v is a vector. Okay, and with this setup, I can write the general form of the Hamiltonian formulation of the equations of motion. So this will be the z dot of t. So now I assume that the z is a 2n dimensional vector of positions and velocities depending on time, okay? And here I have to generalize this J matrix, and what I do to the J matrix is I upgrade it like this. So instead of the ones, I put their identities, okay? So this guy, oh, sorry, I didn't mean to delete it, I meant to highlight it. This is the identity, n by n identity matrix. This is just minus n by n identity matrix, okay? And this gets multiplied by, guess what? The gradient of the Hamiltonian at z of t, okay? So it looks pretty much the same thing like this thing here, except that it's all generalized to vectors, okay? And I can again say that this matrix is still going to be called J, okay? Now it's a 2n by 2n matrix, kind of funny kind of matrix, but that's what gives us the equations of motion in Hamiltonian form.
Question. On that J matrix, you have the 0 and then the I, which is the identity matrix. Is it meant to be a matrix of zeros? Am I just
Oh, yes. Okay, yeah, sorry, I was a little bit sloppy explaining that. So you're right, this is an n by n oops, okay, let me write it properly. You're right. This is n by n matrix of zeros. This thing is the same thing, okay? So this is also n by n matrix of zeros. This is also n by n matrix, but that's the identity. So also zeros except for the ones on the diagonal, right? It's also n by n zeros except for minus ones on the diagonal, okay? And why this works is that because this thing, I can also write it like 0. This is basically to make the matrix vector multiplication work, right? Because the gradient is the gradient of the Hamiltonian, that's what we worked out here, right? So this is the gradient of E as x of t, right? And here is just the v of t. And again, this z dot, if you want, I can write it out here like x dot t and v dot t. Okay, so this is just like writing. So you can immediately verify that this is just rewriting of the Newton's equations of motion in this special form. And that form will be useful for us to talk about energy conservation and symplecticity. And those things are important because they determine, or they strongly influence properties of numerical integrators, okay? And that's essentially what the rest of physics-based animation will be about, because this case of being able to work out an analytical solution, that's only possible for these really simple toy cases. In practical cases, you will have to go to numerical integration, but the good numerical integration techniques preserve certain properties of the exact solution. So that's why I'm working out this Hamiltonian formulation. So I can, next time, I guess I will do it probably on Thursday already, to tell you what is the symplecticity, what is energy conservation, and then we move to numerical integration. All right, so that was to wrap that up. Any more questions?
Yeah, I guess I don't see where energy conservation is being enforced. If you had a non-conservative system, could you consider friction a sink or something?
So the question is where non-conservative forces will be taken into account, or?
Like where are we enforcing conservation?
Oh, okay. So the energy conservation is, or the fact that the forces are conservative is implied already by the Hamiltonian formulation, because it assumes there is the potential. It starts with the potential. So the forces are defined as the negative gradient of the potential, so they are automatically conservative. So this formulation does not allow non-conservative forces. So if you want to model effects like damping, dissipation, you need to extend this model. This model only captures Hamiltonian systems which conserve energy. We will talk about how to do damping and these things later. That's a good question. Thanks. Any other questions? All right. So in that case, we will stop here.